So now that we have all sort of our different types of energy here, at least quite a few of them, and we've talked about conservative and non-conservative forces, what we really want to come up with is our full definition for conservation of energy. Conservation of energy is, in conservation of energy, the total energy in any process is constant. It may change form from one thing to another, but it will always remain the same. Another way to say this is energy is never created nor destroyed, it just remains constant. So the things we have that we know about now, we could have kinetic energy. Let's call that initial. We could have potential energy, right? That takes care of our mechanical energy. We could have our non-conservative forces. So I'm going to say work from a non-conservative force. So for example, work done by friction. Plus, I'm going to add a new one here, other energy, initial, so that we can cover any other type of energy that may be present, equals kinetic energy final, plus potential energy final, plus other energy final. So you'll notice the only difference from one side of the equation to the other is this inclusion of non-conservative forces over here with this work component. And what that's going to cause is, let's say we have friction involved, and we started out with some potential energy, let's call it spring potential energy, pushing something along, but there was friction there. I'm not going to get as much kinetic energy over on this side as possible. So this non-conservative force is going to kind of take away some of that energy that we could have had. This other form of energy here and here can include things like chemical potential energy, maybe from a food source or something, if we're talking about a biological thing. It could include things like electric energy, nuclear energy, energy from radiation sources, anything. So it's kind of, these other energies are kind of a catch-all for anything that we haven't talked about yet, and anything that doesn't fit the category of non-conservative work or of mechanical energy. So let's work a quick sample problem here to kind of figure out some problem-solving strategies here. So we have a spring with a spring constant of 700 newtons per meter. Is going to launch a 0.5 kilogram object in the air. Our first thing is we want to know what is the maximum height the object reaches. So we start with our conservation of energy equation. So kinetic energy initial plus potential energy initial plus any non-conservative work being done plus other energy equals kinetic energy final plus potential energy final plus other energy final. So now we kind of look at this equation and we see what we can eliminate based on what's in the problem. Usually we'll be able to eliminate a lot. So initially, if the spring is sitting there compressed, then it's just sitting still. So we have no kinetic energy initially. There's no mention of any friction or air resistance or anything in this problem, so you can safely assume that our non-conservative work is going to be 0. And there's no other energies present, so we can actually cross that out on both sides. In the final part of our equation, the right side of our equation, we're talking about when the object is at its maximum height. Remember, when an object is at its maximum height, its velocity is 0, and that's, since we're launching this straight up in the air, we can assume that that's 0. And so all we're going to have there is gravitational potential energy. So what this tells me is that my initial potential energy, which is in the form of spring potential, is going to equal my final gravitational potential energy. So 1/2 kx squared is going to equal mgh. So 1/2 of 700, and we have a compression of, that disappeared from my problem, but we're going to say that it was compressed 5 centimeters. Okay. So if it's compressed 5 centimeters, that's 0.05 centimeters squared equals our mass, 0.5 kilograms, times gravity, which is 9.8 meters per second squared, times height. So if we go to solve for height, height will equal 1/2 700 newtons per meter times 0.05 meters squared over 0.5 kilograms times 9.8 meters per second squared. If we put that into our calculator and solve, we get 0.1 0.18 meters. So this is going to launch our half-kilogram object about 18 centimeters into the air. So we'll erase that and talk about the second part of the problem, how fast we're going when it is just released from the spring. For that I'm going to draw just a quick little picture here. So we have our spring that's compressed and our object on top of it, let's say it's a ball, being launched up in the air. And then when it's just uncompressed, when it's just released from the spring, we're going to have something like that. If we said we compressed it by 5 centimeters, then that means there's a 5 centimeter difference in height between this point and this point. So if we look through our problem, we're still going to have no kinetic energy, because that's right here when it was just compressed and there was nothing going on there. We do have spring potential energy. We don't have any non-conservative forces. We don't have any other energies. We do have some initial kinetic energy, or I'm sorry, some final kinetic energy. It is going to be moving at this point. We are also going to have some gravitational potential energy because I'm no longer at what I call the height of 0. I'm now 5 centimeters above it. So I'm going to have both of these two types of energy, and I'm also not going to have any other final energy. So let's kind of put it together here. We have spring potential energy on the left side of our equation. We have kinetic energy final plus potential energy final, which was in the form of gravitational potential energy at that point. So our final gravitational potential energy. So spring potential energy is 1/2 kx squared equals 1/2 mv squared plus mgh. So we have 1/2 700 newtons per meter times my compression 0.505 meters squared, if we convert that to meters, 1/2 my mass 0.5 kilograms times v squared, we don't know v yet, plus mgh, so 0.5 kilograms times my 9.8 meters per second squared times that height of 0.05 meters. If we go through the algebra, I'm going to go ahead and kind of skip to that step. We should get an initial velocity of about 1.6 meters per second. And that's how fast it would be going as it's just leaving contact with the spring there. The last thing we want to talk about today is efficiency. Efficiency is sort of our measure of how much work that we're putting into it versus how much work is actually being used to do what we want to accomplish. So for example, if I have a car engine and I put a certain amount of energy into that car engine through gasoline, how much of that energy is actually being used to make that car go forward? The equation for efficiency is that efficiency is equal to, what we're going to say is useful energy or work output. So there's how much energy or work we get out versus how much total energy we put into our system. So we could write that as maybe work out divided by the energy that's put in. So the amount of work that actually comes out of our system that's doing what we want it to do versus how much energy that we put in. Just for a couple quick examples here, we talked about a gasoline engine in a car. A gasoline engine in a car is only about 30% efficient, and we're working with percents here, so we usually report this number as a percentage, convert it to a percentage. So that means only about 30% of the actual chemical energy that's stored in gasoline is being used to make the car go forward, to do what we want. The rest of it is being lost to heat and other sources like that, friction, other things like that. Compare that maybe to an electric car engine. If you look at the amount of electrical energy stored in those batteries and what gets put into the car, an electrical engine is actually 98% efficient. In other words, 98% of that stored chemical energy in the batteries is being used to make the car go forward. A couple other interesting ones here. If you're swimming on the surface of the water, your body is only about 2% efficient at doing that. So that means only about 2% of the energy you're putting into trying to go forward is actually making you go forward. The rest is heat losses. It turns out there's usually a lot of heat losses within your body in any activity. For example, weightlifting. The amount of energy that your body's putting into getting that weight up, only about 9% of it is being used to actually get the weight up. The rest of it is for all the processes that need to happen in your body to do that. Only about 9% of it actually goes into picking the weight up.